Hi, welcome to topic 2.6. This is gravitational force. We're continuing to talk about unit two, the dynamics equation. So the way you think of it, or not equation, but topic. So the way we think about this is a lot of Newton's laws. And so here we're going to now start talking about specific forces and how we handle them when we talk about Newton's laws. Okay. So gravitational force, this is known as Newton's law of universal gravitation. And what it does is describes the gravitational interaction between two objects. And so what we say is that the objects or systems are directly proportional to the mass and inversely proportional to the square of the distance. So for this reason here, so inversely proportional to the square of the distance, okay, that's what we call this an inverse square law. So what happens is if you were to plot like F versus R, you would go in an inverse shape, but quickly, right? So faster than if it were just an inverse. So the equation is F sub capital G equals G M1 M2 over D squared, or sometimes you can call it R squared. So sometimes they'll call this R squared. If you were to take electricity and magnetism for physics C, you'll find that there's another equation that looks very similar to this called Coulomb's law. In fact, they say that Coulomb essentially plagiarized Isaac Newton. And so there's a lot of comparisons drawn between gravitational force and the electrostatic force. Now, the question is, what is G? Well, G is not 9.8. It is called the universal gravitation constant. And the value is 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. I had the electricity and magnetism equation stuck in my head. So here are some facts about gravity. So the first fact is always attractive. So what is happening is that the force is always pulling into, it's always trying to pull objects down, okay? The force is exerted along a line connecting the centers of mass of the two interacting systems. So like if you're looking at up here in the corner, right, we're looking at gravity, the F gravitational of the Earth by the moon, and then the F gravitational of the moon by the Earth. Well, notice that where the arrows are starting, they're starting in the center of the planet. They're not starting on the center. So if you have to do anything with planets, you would have to find what is called the orbital radius. And so you would just say it's the radius of planet plus the height at which it is away. Sometimes the question will say that the center of mass or the distance between the surface and the center of mass is negligible. So you just say, okay, they're separated by 2 meters, right? That's what happens if you do it with like a person or two people. And then we just say the force on a system is considered to be exerted on the center of mass. Okay, that kind of builds upon the previous one. So one thing to note is that it is a field force. So what it means by field force is that the second you enter into a planet's gravitational force, you are now experiencing that force, okay? And that field has a magnitude here on Earth of 9.8 newtons per kilogram. Okay, some questions you can simply call it 10 newtons per kilogram, especially on multiple choice questions, but the 9.8 newtons per kilogram is what we call gravitational field strength. And it has a magnitude, right, that we talked about earlier of the weight of an object. So gravity is the force that causes weight. It is not the force that is drawn on a free body diagram. Gravity is, or the weight is the force that is exerted on an object. Okay. Common questions in this topic, right? You could get, this kind of question here. They love questions here. What happens if you double the mass of a planet and have the radius? What happens to, the gravitational pull? You can also use this equation, set it equal to the weight, okay, and then do some canceling, and you can get an expression for the G value on any given planet. In fact, this is what NASA's been doing until they were able to, use more sophisticated devices. And then the other question is apparent weight. So apparent weight are elevator questions. And so basically an apparent weight is the gain or loss of weight based on accelerations. Okay. In fact, I think that's going to be our example problem is apparent weight. And so if you were to do the free body diagram, right, you would have FG prime, where the apparent weight actually comes. So like if you look at the elevator, it comes from the normal force or the spring scale that the person is standing on. Then you would have FG, but it would be accelerated up or down. And so you end up with something that looks like FG prime equals M times G plus or minus A. Okay. And that plus or minus A is all dependent on which way the object is accelerating. Okay. And that prime notation, that tells us, this right here tells us that it is an apparent weight, not the actual weight. All right, so let's look at an example problem. A student stands on a bathroom scale in an elevator at rest on the 64th floor of a building. The scale reads 836 newtons. So that is their actual weight. So their actual weight is 836 newtons. As the elevator moves up, the scale reading increases to 935 newtons, then decreases back to 836 newtons. Find the acceleration of the elevator. And then part B says, as the elevator approaches the 74th floor, the scale reading drops as low as 782 newtons. What is the acceleration of the elevator? Okay. So what they do, this 935, that is our apparent weight. So as it's accelerating, we're gaining weight. And so what we would do FG prime minus FG equals MA. And so we want to solve for A. So we get FG prime minus FG over mass. So we need to figure out this person's mass. We'll use 10, right? Because all we have to do, if we want to know what is the mass, we do 836 divided by 10. So it's 83.6 kilograms. So I'm going to do 935 minus 836 divided by 83.6. And there we get an acceleration of positive 1.2 meters per second squared. So when you're accelerated in the positive direction, you're going to feel heavier. Sometimes you get an elevator, you feel that sensation. Oh, I feel lighter. Oh, I feel heavier. Well, the reason is because of you're gaining or losing weight based on the acceleration of the system. Now let's go over to the other side. What happens when we lose weight, right? So our equation is going to be the same. So all of our work is going to be the same thing we have on the right-hand side, or excuse me, left-hand side. So we're going to do FG prime minus FG divided by M. So in this case, we're losing weight, not 860, it's 836. Okay, and then we're going to divide that by 83.6. And so what do? We do 782 minus 836 divided by 83.6, and we get an acceleration of negative 0.65 meters per second squared. So what does that mean? When you're accelerated in the negative direction, you're going to feel lighter. So sometimes when you're into these big high-rise buildings, the elevators go so fast and they slow down so fast, right? Or they accelerate fast and they accelerate slowly, right? Well, you get that like light feeling in your stomach. Okay, that's when you feel like you've lost weight. So when you accelerate positively, you gain weight. When you accelerate negatively, you lose weight. Okay. All right, so that's going to be the end of this video, which is gravitational force. So the next one's going to kind of be a big one. That's going to be our static and kinetic